Hi dear students, welcome to the next topic, and this is the last topic from the chapter dual nature of matter and radiation. When I start the chapter itself, I told it dual nature means there are two natures, both for matter as well as for the radiation. Radiation means light waves. So we are going with the last topic, and this topic is also proves that the electron or the particles will also have a wave nature. And this experiment, which is a kind of an experiment, and this experiment is called Davison's-Germer experiment. So please write down the heading on your notebook: Davison's-Germer experiment. Davison's-Germer experiment. Okay. So what is this experiment is talking about? Before going to the experiment, we already learned about the de Broglie concept. What is the de Broglie concept is told? De Broglie concept is, I can say in a plain way, de Broglie is explained about the wave nature of a particle. So it is defining a parameters called wavelength. If any particles will have a wavelength is available, then we can say which is showing a wave nature of the particle. Okay, this is what is actually de Broglie is trying to prove, and according to the de Broglie and given a set of equation, lambda is equal to h by me, lambda is equal to h divided by root of 2 me, E is the energy. Okay, so these expressions in which de Broglie is given to us. So let's summarize the points. And de Broglie, okay, so de Broglie proves that there is a lambda for all particles, for example an electron, for all particles, example for electrons. So electrons will have a de Broglie wavelength which is available for an electron as well. So he is defining the de Broglie wavelength, lambda is equal to h by mv, which is equal to h divided by, this is called momentum is 2 root of 2 me in energy, and h divided by root of 2m if it is electron, then ev. Okay, qv, energy is qv, so ev. And we finally solved an approximate formula. I hope you remember, 12.27 divided by root v. This is an approximated formula, root 150 divided by root v. So 12.27 divided by root v. The previous lectures we have seen this formula. So what it is indicate, if you are giving a voltage over will be here, a voltage. This is a voltage, this is velocity, but this is voltage. Do not confuse between these v and this v. This is energy, momentum, this is momentum and energy relation, and energy is root of 2m ev. E is equal to qv, q is electronic charge, so it ev, v is the voltage. So we got this formula. Hope you remember from the last session. Or if you turn 1 or 2 pages back on your notebook, if you have regularly writing the class notes, definitely you can see this on your notebook. So lambda, so we know the value of lambda, we can find out if voltages will be given, and we can find out the values of lambda. But there is Davison's and Germer, these two scientists proves that, these scientists in additionally prove that what Davison's, so Davison's and Germer proves that the fastest moving electrons, we know electrons are already fastest moving, it's not slow moving. Fastest moving electron can exhibit wave nature, Okay, so this fastest means just it is specifying like it is fastest. We know it is fastest. We already know it is fastest, and there is no need to specify. It is saying like it is a fastest thing. Okay, so electron is, of course, it's moving in a fastest way. So this is actually they specified in the year of 1927. In the year 1927 this specified, and later J.P. Thomson Thomson, AP Thomson's also proves this concept. That is in 1928. If I remember correctly, he got a Nobel Prize for this one, for this giving I can say by giving a more clear explanation for this one, and he got a Nobel Prize. Nobel Prize actually, this is GP. I written my code, right? GP Thomson is also post 1928. Actually, this Nobel Prize will be false over here. This is a Nobel Prize which is winning over here. But later in 1928, this invention is also happened, and actually this is a one Nobel Prize and which is shared between these two. Okay. But actually, whom get the Nobel Prize for proving the wavy nature of the light means, I can say, first I can say Davison-Germer experiment, because this is happening after 1 year. 1927, first the Davison-Germer conclusions are came. Then after that only 1928 this is happening. Let's see what this Davison and Germer done and what magic, how they have proved this concept. So let's see that. Okay. Fine. So let's see his experimental step. It's quite easy. Okay. So let's go ahead. Okay. Listen very carefully. We are explaining about the diagram, and we have some tungsten filament, and this is connected to a battery. Okay, and there is some coating will be there. This is a barium oxide coating, and we have a cylindrical metallic cylinder, and this is connected with an HT. I'll tell you what all these things are. So we have a nickel material over here. Then to catch it, we have a detector over here. Detector, and which is mounted over here, for example, with some piston it is mounted over here. So I'll tell you, this is I'm writing as listen very carefully, this is I'm writing as LT. In LT in physics it is called low tension. Low tension means low power battery. That's the meaning, low power battery, and tension means voltage, low tension. Tension is a very common unit which is using in the electricity board people, I mean the lineman and the assistant engineer. So these guys will be using. So low tensions. So low tension battery. So this battery will be given. This is a tungsten filament. Let me mix with another color. So this is the tungsten filament. So tungsten filament will be heated up if you are continuously giving a voltage. And this is a coating actually which is given over the tungsten filament, and this is a barium oxide coating. Okay, so what will happen now? Now you are giving a battery and connected to tungsten filament. Tungsten filament will be heated up, and it is connected with a barium oxide coating. So due to this one, the electrons are emitted from the barium oxide. Now we have a metallic cylindrical structure, metallic cylinder will be there, and this is connected with HT. HT means LT in the opposite, high tension. This is low tension, high battery. So what will happen if you are giving high battery, high electric field will be there. These electrons will get accelerated. So I can say this is an accelerated electron. So this accelerated electrons will move over here, and this is a metal of nickel. Okay, this is what is arrangement, nickel crystal. So what will happen? These electrons will hit over here, and after reflections it will scatter into all the areas, right? Suppose I am assuming, and these electrons are scattering to all the side, these electrons are getting scattering. So what will happen? We have a detector over here and the detector is equipped with a film. It's a kind of an X-ray film. So a film will be there and we have a detector will be here. Okay, the presence of this detector this is not a fixed one, and it is a kind of, I don't know how to draw it, it is a kind of a movable detector. I can say this is a movable one, and this is like this kind of structure. So this can be easily rotated in the sense this can be rotated from here 0 to 180 degree. This can be easily rotated from one point to another point. This can be easily rotated, this detector. Okay, so we have an incident electron over here, and we also have the reflected electrons over will be here. So what we have seen is like barium oxide is coated on the tungsten filament, so this will emit the electron in the shoot way, and we are giving a high tension voltage, and because of the high electric field it is again speed up. It is hitting on the nickel crystal, and we will have a reflected electrons over here. So this was the structure. So what he is observed in his observation is that this detector, listen very carefully, this detector can be easily movable like this. So what will happen? This is a high tension voltage. High tension voltage means we are assuming this can be changes from 0 to maybe some 100 kilovolt. Okay, it can be go to high range. That's the meaning. So what we have seen is like we place the detector here. Slowly moved, electrons are coming from there, no problem. Slowly moved, and keep it will be here. So it will be complete one rotation. So if you complete one rotation, in that cases, if you look into the film, okay, if you look into the film from the detector, what you can see over will be here means there is a big crowd of electron. Then the crowd of electrons will be lesser, then there is again a big crowd, then there is a big crowd, here also there is a big crowd, then it will be less. Okay, so it is something like this one. So if you look into this diagram, for me this looks like a peak, a low, a peak. Okay, something similar to this one. So this low indicate the presence of electrons are very low will be here, and the high peak, high concentration indicate more electrons will be there. Okay, so electrons presence are more will be here means, or it is a kind of a pulse or peak you are showing means, in physics it is called constructive interference. In the wave optics chapter we learned very detail about it. So it is called constructive. Constructive means one electrons will have one wavelength, so it is moving. Another electrons will also have another wavelength. It's both crusts are joining, then we'll get a peak. Both trough are joining, then we'll get a downside. Okay, so what he told is like I can see in the screen a kind of a wave nature, a constructive and a destructive and a constructive interference kind of pattern I can see. Okay, this is one side, right? Both side also we have a constructive and a destructive patterns will be here. This indicate electrons exhibit what nature? Wave nature. Okay, so electrons are coming in a constant interval, but at some point a constructive interference are happening. One crust with another crust are joining, so I will get a big crust. Another trough is joining with another electron trough, so I will get a deep trough. So how this crust and the troughs are happening? The crust and the troughs are only happening in wave particle, or a particle will having wave nature. So this is the way he proves that okay, D. Broglie, whatever you told is correct. According to my experiment also, I can prove that light is exhibiting, or the particle like electron exhibiting wave nature, because I can see in my screen constructive interference, I can see in my screen destructive interference, it is like a wave. So one of the observation, so hope this diagram is clear, you have to definitely draw and understand the concept. Okay, so hope this concept is clear to you. Next, we are going the analysis of this one. What is this analysis? Whatever you understand from my description, pause the video and write it in your own sentence. Okay, anyway, we are not going to do any beautiful sentences, we are not formulating. Whatever you understand, that is the explanation for the diagram, but the main key points will be here. Whatever he told is we are used a nickel crystal will be there, a nickel materials will be here. Okay, so what happened means in case of a nickel, so in case of a nickel crystal or in any crystal, there is a lattice structures will be here. There is a lattice structure. Okay, now the condition, suppose the one electron beam come here and going like this one, another electron beam come here and going like this one. Okay, now this is a kind of, this is a lattice structure. Lattice structure means every nickel atoms are will be here, and nickel atoms or the nickel atomic particles are located over here. This is a lattice structure, right? In chemistry also you will learn like this structure, right? For silicon and for germanium. So same way, this is a kind of a three-dimensional structures, but this is a kind of a two-dimensional structure. And the distance between the two lattices or the crystal lattice called D. Okay, next, suppose I am saying like constructive interference are happening, destructive interference are happening. There is one conditions will be here to happen constructive interference. Constructive interference what is the meaning? One electron is moving like this, another electrons are moving maybe the same way. So these two electrons are added up. How should I get? I will get like this. So this plus with the plus, minus with the minus, and it will be get added up. Okay, so this is the way constructed. So the constructive interference, they indicate the path difference. Path difference means if you look into these two things, what is the path difference? Path difference means distance, the difference of distance between these two. There is no difference starting from here, plus plus, minus minus, next plus, next 0. So all are aligned. So I can say path difference in the path equal to 0. Path difference equal to 0. For example, I can make it more clear. Suppose you are starting from the point A, you are going to the point B, you traveled 10 meter. Okay, one of your friend is starting from C and he is going to the point B and he traveled 25 meter. What is the path difference? Path in the difference, ivarku 10, ivarku 25. So this much is the path difference. Path difference is 15 cm. How much he traveled extra, that is called path difference. So path difference equal to 0. This is one case. In another case, listen very carefully, this is one wave. I make the wave starting from here. So now also plus with the plus, minus with the minus, but this much path difference will be here. This much path difference means this is how many lambda? 1 lambda. So if path difference equal to 0, constructive interference. If path difference equal to 1 lambda, constructive interference. Similarly, path difference equal to 2 lambda also, plus with the plus aligned down, minus with the minus aligned down. Okay, again with the 3 lambda edutana, idipo 1 lambda. Inipo I am drawing the next word. So this is actually starting from here and completed over here 1 lambda, and this is 2 lambda and continuing. So I am putting the next wave. Next wave will go like this one. So if you see, this is 1 lambda up to here, and this is the next lambda. So this is again one more lambda. So total path difference is how much? 2 lambda between the first wave and the second wave. Still it is happening what? Constructive interference. To happen constructive interference, either path difference equal to 0, or path difference equal to 1 lambda, or path difference equal to 2 lambda, or path difference equal to 3 lambda. I can say in general path difference equal to n lambda. Value of n is will be 0, 1, 2, 3, etc. Okay, if these conditions are happening, then I can say path difference. Now these are the two electron beams which are coming from the crystal. So this wave is traveling like this one, and this wave is traveling like this one. So how much is the distance travel? If I draw one line over here, whatever I have marked will be here in this red big line. This is the distance extra it is traveled. Okay, so this is the extra distance these particles are traveled. So this distance we have to calculate. This distance is actually called the path difference. Understood? This distance is actually called the path difference. So path difference means with respect to the first ray, the second ray traveled this plus this. So I'll just mark it as A, B and C. So how much this extra will be traveled? The path difference equal to n lambda. So path difference is AB plus BC equal to n lambda for constructive interference. Destructive വേറെ കേസിലുണ്ട്, that I will tell you bit later. Okay, while you are learning about wave optics, you will understand that, but now we will only focus on the constructive interference. Okay, of course it should have constructive interference and destructive interference. Interference means addition of two waves, that is called interference. So AB plus BC, I know the crystal distance, crystal lattice distance. What is this distance? Is called D. Okay, if the angle of incidence is, maybe let me make it as 5 by 2. So this also 5 by 2. This crystal white is create an angle theta. So this angle is also theta. Now this area alone, I am just zooming and drawing it over here. Okay, so the first ray coming and going like this. Second ray coming exactly and going like this one. So now we will make this area, I zoomed out like this one. So I know this angle is called theta. So we have a line and this is called D. Okay, so we have a perpendicular line to this one. So we know this is 90 minus theta. If this is 90 minus theta means this is theta. And what is this value will come? 90 minus theta. So what is this side will come? This side is D. So D ന്റെ പക്കത്തിലിരിക്കുന്ന side. So D into cos of 90 minus theta. This side. Same way this side also. Okay. So this side also angle of emergence theta is, this is theta, and this is how much? 90 minus theta. So this side is also D into cos of 90 minus theta. Angle of incident is equal to angle of reflection, right? Basic rule of law of reflection. So that is with respect to normal, correct only. That is with respect to with respect to normal, angle of incident equal to angle of reflection. So if that is two are equal, this is also equal. Okay, so what is the path difference? AB plus BC. This is called our AB, A to B to C, and this is called our BC. We'll substitute. What is cos of 90 minus theta? Cos of 90 minus theta is sin theta. So I know, so D into cos of 90 minus theta plus D into cos of 90 minus theta, and this is equal to n lambda. So I can say D cos theta is sin theta. So 2D sin theta is equal to n lambda. This is a most famous equation, and this equation is derived from the Davis-Germer experiment. This is called Bragg's equation. Very important. Okay, questions may come. So this is called the Bragg's equation. The Bragg's equation 2D sin theta. This is with respect to a crystal, and D is the crystal lattice structure. Very important. Theta is the angle between the lattice plane and the incident. It is not this 5 by 2. This total angle is 5. So 5, it is not 5. It's very important. It is called the theta. So definitely if they're asking any question from the Bragg's equation, they will give you the value called 5. So you have to find theta. Okay, so you know the total angle is 180 minus 5. If you divide, suppose if phi equal to 60 degree, then 180 minus 60, how much will come? 120 equal to divide. So this is 60. So definitely they will give you the value. So this is the Bragg's equation, and based on the Bragg's equations we have to do this one. So okay, so remember the Bragg's equations. Hope you understood. The two waves will have the path. This is the extra distance traveled by the wave, and this distance is equal to n lambda. Then that is a condition for a constructive interference, and this equation is called Bragg's equation. Very important, Bragg's equation. You will get some problems based on this one. Okay, so let me see how this will help us. Why we have done the Bragg's equations from the Davis-Germer experiment. Okay, now one of the observation is like this one. When the high tension voltage when the high tension voltage V is equal to 54 volt, and we know the angle of what we say, the angle of deflection. I can say angle of deflection in the sense what is this phi indicate means whenever a light ray hitting on a nickel crystal, and this is the nickel crystal, and it is coming to where? It is coming to our it is coming to our detector. It's coming to our this angle is called phi. This angle is called the phi. So phi means nickel crystal hit the detector angle on phi. So when this V is equal to 54, this is an experimental observation, phi is equal to 50 degree, we can see maximum constructive interference. Okay, so the constructive interference can be happen n is equal to 0, n is equal to 1, n is equal to 2, 3, 4, 5, etc. So let me take for a nickel crystal, for different crystals will have a different values over will be here. So this the value of phi will be equal to 50 degree we know, but of course we know this total value. So I know theta plus phi is equal to 180 degree. This is one way. Or if I am taking the half of this one, I can also write theta plus phi by 2 equal to 90 degree. Now I will substitute for theta. Theta plus 50 divided by 2 is equal to 90 degree. So theta will be equal to how much? Theta plus, so this is 25. So 90 minus 25. So this will becomes as theta equal to 65 degree. So all these values will got. And for nickel crystal lattice distance അത് നിക്കൽ ക്രിസ്റ്റലിൻ്റെ സ്റ്റാൻഡേർഡ് വാല്യൂ ആണ് 0.91 ആങ്സ്ട്രോം. അത് ലാറ്റിസ് ക്രിസ്റ്റലിൻ്റെ അല്ലെങ്കിൽ നിക്കൽ ക്രിസ്റ്റലിൻ്റെ ലാറ്റിസ് ഡിസ്റ്റൻസിൻ്റെ സ്റ്റാൻഡേർഡ് വാല്യൂസ് ആണ് വാട്ട് എവർ വി ഹാവ് റിട്ടൺ ദർ. ഓക്കെ, ഫൈൻ. So I need the space of Brainiacs equations will be there. Okay, so let's remove. So we know all these values. Now we'll substitute in this one. 2d sin theta is equal to n lambda. Let's take n is equal to 1. If n is equal to 1 case, first lambda means 1 lambda difference. So 2d into 0.91 angstrom into 10 power minus 10 into sine of theta. Theta is 65 degree. Sine 65 divided by 1 is equal to lambda. If you do this one, we'll get a value of 1.65 angstrom is the value of this lambda. This lambda value in this case lambda equal to 1.65 angstrom we got. And as well as, okay, so this is the we have fixed the high tension voltage 54 degree and phi is equal to 50 degree. അതേ ഒരു എക്സ്പെരിമെന്റിൽ ഇതിന്റെ വാല്യൂസ് എല്ലാം ഫിക്സ് ചെയ്തു. Then ഈ value we are substituted in the Brainiacs equation, and from the Brainiacs equations we got a value of lambda equal to 1.65. Then what we have done means, okay, Davison-Germer is also told, oh, it is similar to the Brainiacs, or it is similar to the de Broglie equation, right? We have a de Broglie formula, 12.27 divided by root v. So we have a value according to, so this is actually a de Broglie equation. So this is a de Broglie equation. 12.27 divided by root v. V is how much? V is 54 volt. If you substitute it here, we'll get 1.67 angstrom, approximately equivalent. So what we have seen is like the understanding will be here. De Broglie also get one value, Brainiacs also get one value. I can say Davison-Germer experiment along with the Brainiacs formula, Brainiacs equation proves that de Broglie is correct. Proves that de Broglie is correct. De Broglie correct aanennu Davison-Germer experiment is proved. Through the Davison-Germer experiment we got a new equation, and which is called the Brainiacs equation, and with while if you are giving the a certain value, we fixed for voltage and we fixed for the angle, our values we are giving into a Bragg's equation, we got lambda. Same voltage we are substituted in this so the values which we have substituted through the Bragg's equation, we got 1.665, and through the values we got in the de Broglie 1.65, both are approximately equal. This proves that de Broglie is correct, Davis-Germer is correct. From the understanding from the Davis-Germer, Bragg's equation is derived, that is also correct. Light or the radiation or the electron possessing what kind of nature? Wave nature. This is a final conclusion. So we already know electron or the subatomic particles also exhibit what kind of nature? The subatomic particles are exhibiting particle nature. In addition, Davis-Germer along with the de Broglie also proves that this is a kind of wave nature, particles also are experimenting. So very important, from this formula I can write, listen very carefully, a final conclusion: 2d sine theta divided by n. Okay, 2d sine theta by n lambda, which is equal to 12.27 divided by root v. This is applicable for, actually this formula is applicable for electron. If some other particles are coming, as I told, root v you cannot apply because this is a standard values for electron. So this is a final conclusion, which means you can club the Bragg's equation, the de Broglie equation, Davis-Germer. Everybody finally belongs to a single family. That single family is called wave nature of the particle. Hope you understood my sessions on this one, dual nature of matter and radiation. Chapter theoretical parts will be over, and we'll see on the subsection, the next sessions, on the question discussion of this chapter. Okay, so thanks a lot for watching this video. Have a great nice study time. Bye.